Okay, keep going. So number 10, the pressure of an electron degenerate gas should depend on the number density and the mass of an electron, ME, and Planck's constant. Use dimensional analysis to derive the pressure of an electron degenerate gas. Okay, so we're going to set up our equation saying that pressure is going to go as our number density to some power, mass of the electron to some other power, beta, and Planck's constant to gamma. It's totally fine if you want to use A, B, and C instead of alpha, beta, and gamma. Okay, so then let's look at the units for each of these. So we have pressure is force per area. So this is a Newton per meter squared. And a Newton is a kilogram meter per second squared. I'm going to divide by meter squared. So I get a kilogram meter to the -1, second to the -2. So my dimensions, kilogram goes to mass, meters goes to length, and seconds goes to time. Okay, and then we have our number density. So this is like a number per volume. So 1 over volume would be 1 over meters cubed. So our units for that, or dimensions, sorry, would be length to the -3. And then we have Planck's constant, h bar, so that is a joule per second, or joule times a second, I'm sorry. And a joule is a Newton meter times a second, and then we go ahead and do our Newton again, is kilogram meter per second squared for a Newton times a meter times a second. So I get kilogram meter squared, and then second divided by second squared gives me a 1 over second. Yeah. So then if I go to dimensions now, kilogram becomes mass, meter squared becomes a length squared, seconds to the -1 is t to the -1. So now we're ready to plug in our dimensions on each side of our equation. So my pressure comes down on the left side, so that's going to be mass, length to the -1, time to the -2, right? So that's my pressure. Okay, and then I'm going to do my number density up here. So my number density is in length to the -3, and then that's going to the power of alpha. I plug in for, I didn't do the mass of the electron, but that's just a unit of mass. So that is just m to the beta. And then we have h bar, which is a mass length squared t to the -1, and that's all to the gamma. So let's distribute in our exponents here. So we have L to the 3 alpha, M to the beta, and then I distribute my gamma into each term. So M to the gamma, L to the 2 gamma, and T to the minus gamma. Whoa. Not sure what I did there. Okay. All right, and then we want to combine our like terms. So we can combine, let's say, all the terms for length. We have 2 gamma minus 3 alpha. And then for mass, we have beta plus gamma. And then for time, we have minus gamma. And then we bring down what we started with for pressure, mass, length -1, t to the -2. Okay, so our easiest equation to deal with right now is the time. So if we look at our exponents of time, on the left-hand side, right, so I'm just going to kind of skip this, but we have t to the -2 equals t to the minus gamma. So it means -2 equals minus gamma, or gamma equals 2. Okay, and then we can look at, let's look at the mass equation. So my mass equation, on my left side, the power of my exponent is 1, and on my right side, it's beta plus gamma. So I know from the time equation that gamma equals 2, so I have 1 minus gamma equals beta, and beta equals 1 minus 2 equals -1. Okay, and then Finally, we'll do our length. So on the left side, we have length to the -1. On the right side, we have 2 gamma minus 3, alpha. So we know gamma, we want to solve for alpha, so switch sides here. So 3 alpha is 2 gamma minus 1. Alpha is 1/3. 2 gamma minus 1. Gamma is 2. 1/3, which we learned from the time. So 2 times 2 minus 1. Did I do that right? Oh, this is a -1. So negative, negative. So this is a plus. Okay. And this is a 3. So we get 5/3. So my equation for pressure, I'll just put it under here. P equals n to the alpha, so n to the 5/3, mass to the beta, or me, that's as a -1, so that's underneath. And then h bar goes to the gamma, which is squared. So that's my equation for the pressure in a star or an electron degenerate gas. Okay, 11 is pretty quick. Let's do that. Mean free path of a photon inside the sun is approximately 1 centimeter. So that's our mean free path is 1 centimeter, 0.01 meters. And then how many collisions does it take to go from the center to the outside of the sun, right? So we have the photon is going, doing this random walk out to and then it is free to fly. Okay, so our equation from the equation sheet, right, is that the RMS distance that it travels is the square root of the number of collisions times the mean free path, or the distance between collisions. So this is going to be the radius of the sun. And we have square root of n and L. We're trying to find this. So n is r sun over L, and then we have to square that. So if we plug in here, the radius of the sun, 6.96 times 10 to the 8 meters. Our mean free path is 0.01 meters, and we got to square that. And I got 4.9 times 10 to the 21. That is a lot of collisions. So that kind of goes back to the question of who gets out first, right? The neutrino or the photon. So the photon makes all these collisions and it can't get out. Let's stop there.